Welcome back to our series on the AISC 36016 steel I-beam design capacity calculator. In our previous videos, we covered the basics of the calculator and delved into moment capacity calculations. Today, we're going hands-on with two specific design examples, G.1a and G.1b, which focuses on W-shaped beams under strong axis shear. These design examples come from the companion to the AISC Steel Construction Manual, Volume 1, Design Examples. We'll be working through both examples, which involve W-shaped beams subjected to shear forces. Let's look at the details for each example before diving into calculations. So example G.1a, W shape in strong axis shear, given using AISC manual tables, determine the available shear strength and adequacy of an ASTM A992 W24 by 62 with end shears of 48 kips from dead load and 145 kips from live load. So the solution starts out from using the AISC manual, table 2-4. The material properties are as follows: ASTM A992, Fy equals 50 KSI, and Fu equals 65 KSI. So from chapter 2 of ASCE/SEI 7, the required shear strength is, using LRFD design method, 1.2 times the dead load and shear of 48 kips plus 1.6 times the live load and shear 145 kips, which that equals 290 kips. Let's go back to our quick design calculator and enter in these properties. The design method is LRFD, and the member type is a W24 by 62, which we can load that from our database, and the section dimensions are preloaded and reflected in the graphic above. The material properties of ASTM A992 steel is a yield stress of 50 kips per square inch and an ultimate stress of 65 kips per square inch. The design example did not give us any information about the span properties of the member, so I am going to just leave the default values of 30 feet for the unbraced length in the strong axis and 15 feet for the unbraced length in the weak axis. The design example did not have any design loads besides the strong axis shear force of 290 kips. So I am going to change the axial compression into 0 kips, the axial tension into 0 kips, and I'm going to make the shear force about major axis as 290 kips. I'm also going to change the major and minor bending moments to 0 kip feet. Now that we have input our section, material properties, member properties, and design loads and specified our chosen design method, let's run the calculator. The output summary on the right-hand side of the screen shows our utility ratios and capacities. This is also reflected in the comprehensive hand calculation report Each engineering result is given an easy to follow detailed breakdown. I have already downloaded a copy of my PDF report by selecting this PDF report button, so let's take a closer look in a different tab. Alright, I've put the AISC design example side by side with the SkyCiv calculation report so we can walk through the design results. Let's scroll down to the shear capacity about the major axis calculation in the SkyCiv report and follow along with this AISC example. Continuing on with this design example G.1a from AISC manual table 3-2, the available shear strength is V times Vn equals 306 kips, which is greater than 290 kips, so that's okay. So basically the available shear strength is greater than the required shear strength. Going back to the SkyCiv calculation for nominal shear capacity, the nominal shear capacity can be calculated by multiplying 0.6 times the yield stress times the shear area. The yield stress is 50 KSI and the shear area for the W24 section is 10.191 multiplied together, and by 0.6 we get a nominal shear capacity of 305.73 kips, which is similar to the rounded up answer in the AISC design example of 306 kips. Checking the utilization ratio for the 290 kips of end shear, that is the required shear strength, we get a utilization ratio of 0.95. Now, if I were designing this in real life, I might choose a beam with a greater shear capacity because we are designing right up to the capacity of 95% utilization. But for the sake of this design example, this is still passing because the available shear strength is greater than the required shear strength. So this is still an okay and passable design. Now let's move on to example G.1b, W shape and strong axis shear. This example reads, given the available shear strength of the W shape in example G.1a was easily determined using tabulated values in the AISC manual. This example demonstrates the calculation of the available strength by directly applying the provisions of the AISC specification. Solution. From AISC manual table 2-4, the material properties are as follows. ASTM A992 FY equals 50 KSI, FU equals 65 KSI. From AISC manual table 1-1, the geometric properties are as follows. W24 by 62, D equals 23.7 inches, and the web thickness is 0.43 inches. You can see that these geometric properties align with the section properties listed in the SkyCiv report. These geometric properties can also be found in the input summary on the SkyCiv calculation report. Continuing on, let's scroll back to the shear capacity about major axis calculations in the report. The AISC design example solution continues with nominal shear strength, except for very few sections which are listed in the user note. AISC specification section G2.1a is applicable to the I-shaped beams published in the AISC manual for FY equals 50 KSI. The W-shaped sections that do not meet the criteria of AISC specification, section G2.1a, are indicated with the footnote V in tables 1-1, 3-2, and 6-2. Following specification equation G2-2, CV1 equals 1.0, which is also reflected in the SkyCiv report under the nominal shear capacity calculation. Continuing on from AISC specification section G2.1, area of the web, AW, is determined as follows. AW equals depth times web thickness. As you can see in the SkyCiv calculation report, SkyCiv uses the same calculation to determine the area of the web. The depth is 23.7 inches times the web thickness of 0.43 inches, and we get an area of the web that is 10.191 inches squared, which is rounded up to 10.2 inches squared in the AISC design example. Moving on from AISC specification section G2.1, the nominal shear strength is calculated by 0.6 times the yield stress times the area of the web times CV1. As you can see, SkyCiv's calculation report also uses the same equation G2-1 to calculate the nominal shear capacity. This equals 0.6 times 50 times 10.191 times 1. That will get a nominal shear capacity of 305.73 kips, which is rounded up to 306 kips in the AISC design example. As you can see, SkyCiv references the relevant design code and equation in the calculation report, so you are never questioning where a certain equation comes from. Continuing on to the available shear strength. From AISC specification, section G2.1, the available shear strength using the LRFD design method is phi v equals 1. Phi v times the nominal shear capacity equals 1 times the rounded 306 kips, which equals 306 kips of available shear strength. SkyCiv also uses that same equation G2-1 to determine the design shear capacity. We multiply phi v equals 1 by the nominal shear strength of 305.73. Those two values multiplied together equals 305.73 kips, which is our design shear capacity. Both examples illustrate how to determine the shear capacity for W-shaped beams. It's vital to validate these outputs to ensure structural safety and compliance with design codes. In today's video, we worked through examples G.1a and G.1b from the companion to the AISC Steel Construction Manual Volume 1 design examples. They both focused on W-shaped beams in strong axis shear. By using the SkyCiv calculator alongside AISC design examples, we gained valuable insights into shear design. Remember, accurate calculations are critical for safe and effective structural design, and you can count on SkyCiv for that. If you have any questions about this quick design calculator or any of our other quick design calculators or modules, please do not be afraid to utilize this SkyCiv support chat, and either myself or another team member will answer any questions you may have. Thank you so much for watching. If you found this video helpful, please like and subscribe for more tutorials on structural design using SkyCiv tools. Have a great rest of your day.